All right, so let's get started here. So we're going to continue our discussion of chemical structures. Last class we introduced these Lewis structures or electron dot structures. These are these representations of covalent molecules. And we talked a lot about these structures, in particular that these lines, they represent covalent bonds in our molecule. So water, we have hydrogen covalently bound to this central oxygen atom. And each covalent bond represents a pair of shared electrons. So 2 shared electrons per line. There is another type of electron that occurs in covalent molecules, non-bonding electrons. That's what these dots represent. So these were lone pairs in our molecule. All right. And up until now, I showed you these structures, and we talked about these structures, how to count electrons, how to make sure that every atom is happy, has a complete octet. But we don't know how to actually draw them yet. And so that's what the focus of today is going to be. There's one more skill that we need before we can do that. And this is a periodic trend, one of the first ones that we're going to talk about. And by that, I mean a property of elements that we can sort of compare just by looking at the periodic table. This is what's called electronegativity. Okay, so electronegativity is an element's ability to pull electron density in a covalent bond. So what the hell do I mean by that? All right, let's take a look at a very simple molecule here, HF. Okay, we said that this line here represents a covalent bond between the hydrogen atom and the fluorine atom. So this is a shared pair of electrons here, right? That's that one word you want to have in your mind synonymous with covalent bonds is the sharing of electrons. All right. The word sharing kind of sounds like it's this nice, neat, like preschool kind of thing where everybody's happy. Really, these two atoms are engaged in this tug of war over this pair of electrons. Both of them are holding on tightly to this pair of electrons, trying to pull that pair of electrons towards them. Okay. So electronegativity, if we're going to simplify things here, what is electronegativity? Well, again, we have these two atoms that are engaged in this tug of war. It turns out that certain elements are better at tug of war than other elements. All right? Certain elements are better at pulling electron density in this covalent bond. And if we were to look at the actual electrons here, we represent it in our Lewis dot structure, or in our Lewis structure as this little line here. Okay? But it turns out that if you were to really image this pair of electrons here, what you would find is that most of that electron density is actually over here on this fluorine atom. And very little is on the hydrogen atom. Fluorine is way better at pulling that pair of electrons in that bond. So it ends up pulling all that electron density onto itself, leaving hydrogen with very little electron density. Okay? So we talk about sharing of electrons. It is not an equal sharing here. These two elements are engaged in this tug of war, and some elements are better at tug of war than others. All right? It turns out that the absolute tug of war champion on our periodic table here is fluorine. Okay? Fluorine is the most electronegative element. Again, the tug of war champion. Okay? So we can look at the periodic table and we can compare the electronegativity of two elements based on quite simply just how close to fluorine they are on this periodic table. All right? So if I wanted to compare, for example, carbon versus oxygen, and I asked which one is the more electronegative element, you're going to look and you're going to see which one is closer to fluorine. Right? The closer an element is to fluorine, the more electronegative it is, the better at tug of war that it is. So just by proximity to fluorine here, I can say that this one is more electronegative and this one is less electronegative. All right, so comparing electronegativity is going to be, it's a pretty simple first step in our drawing of structures, but an important one here. Again, electronegativity, we can define it here in our chemistry terms. This is an element's ability to pull electron density in a covalent bond. We can think about it a little bit more simply as these two elements are engaged in a tug of war over that pair of electrons, and certain elements are just better at tug of war. Okay. So now we're going to work on drawing these electron dot structures, these Lewis dot structures. All right, so that is going from a formula like CH4 and converting it into one of those Lewis structures. Okay, so step one is we need to total up the number of valence electrons in this compound. All right. We discussed how you can tell the number of valence electrons in an element just by looking at the periodic table. All right, we're going to number our columns. 1, 2. We're going to skip over those transition metals and just keep going. 3, 4, 5, 6, 7, and our noble gases are 8. So if we look at this compound here, we have 1 carbon. Carbon has 4. Plus we have 4 hydrogens. Each hydrogen has 1 valence electron. So 4 times the 1. That brings us to a total of 8 valence electrons for this compound. All right, so when we draw our Lewis structure for CH4, we're going to make sure that we have 8 electrons on the board. Whether they're in lone pairs or in covalent bonds, the total number of electrons that we see in our structure has to add up to that total number of valence electrons. Okay, so step one, as we said, is to calculate the total number of valence electrons in our compound. So CH4, we said that we had 8 valence electrons. All right, so now we're going to start our drawing here. We're going to place the least electronegative element in the center, right? So that's why we had to discuss this electronegativity, because we're going to compare our elements here. Whichever one is the less electronegative one, that's the one that we're going to place in the center. The only caveat here is it can never be hydrogen in the center because hydrogen's so teeny tiny small. It only has it only has 2 electrons in its octet. So we're never going to put hydrogen in the middle. So what we're going to do is we're going to put the carbon in the middle. Okay, now we're going to decorate it with the remaining atoms, right? So now we have these 4 hydrogens. We'll place those all around here. All right, so we have our central atom carbon, and then our substituent atoms, our hydrogens that decorate the outside. And now we're going to connect these constituent atoms to the central atom with a single bond. All right, so for each one of these constituents, I'm going to connect them to that central atom by drawing one of those covalent bonds. Okay, now we've already put some electrons down on the board by drawing those lines in there, right? Each one of those lines represents how many electrons? 2. So we're going to need to deduct from our total here. We had 8 to work with total. We've already put some on the board, so let's count down how many we actually placed on the board here. Each one represents 2, so that'd be 2, 4, 6, 8. So now we have used up all of our electrons here. So we're going to keep track up at the top here and deduct. We don't have any more electrons that we can put down on the board. All right, so at this point we're done putting down electrons here. We're not done yet. We still got to go back and check that this structure is legitimate here. All right, in particular, Do we have any valence electrons remaining? We said no, right? We got rid of all 8 of them here. Okay. So then we just need to make sure that all of our atoms are happy, that they all have that full octet, their full valence shell. We call it the octet rule because how many electrons do most elements want in their octet? 8, all right? There are a few exceptions, and the most important one, because we're going to see it over and over again, is hydrogen. Hydrogen's the very first element on the periodic table. It is very, very tiny. It can only fit a maximum of 2 electrons in its octet. So looking at this structure here, we need to make sure that all of our elements have a complete octet. If we look at our carbon in the middle, it's got 1, 2, 3, 4 bonds around it. Each bond represents 2 electrons. So that'd be a total of 2, 4, 6, 8. All right, so my carbon's happy. If I look at my hydrogen, each one has just this 1 bond associated with it, these 2 electrons. And again, that's all hydrogen can fit in its octet. So indeed, if I look, all of my elements, my carbon in the middle and all my hydrogens on the outside, they all have a complete octet. So now we're done. Okay? So we're going to total up the number of electrons we have. We're going to put down our central atom, put everything else, all the other elements around it. We're going to connect everything to that central atom with a single bond and deduct it from our total here. Okay? All right, so we're going to do a bunch of examples, each one a little bit more complicated than the next here. In this case, after we drew all those single bonds, we had already used up our total number of electrons. All our elements were happy, and so we were done. Okay? All right, so now we're going to repeat the process here, but with a different example. We're going to do CF4. And again, that very first step is to total the number of valence electrons that we have in this compound. So everybody take a second and total up how many total valence electrons we have in this compound here. All right, how many we got? 32. Each fluorine has 7. Our halogens have 7. I got 4 of them, so that's 28. Plus carbon's 4 brings me to a total of 32. All right, now we're going to place the least electronegative element in the center and all the remaining atoms around it. So which one of these is going to go in the center, carbon or fluorine? Carbon. So then we're going to decorate with these fluorines around the outside. Okay, now I'm going to connect all of these constituents, everything on the outside, to my central atom. All right, but each one of those lines that we just laid down represents a pair of electrons. So now I got some electrons on the board here, so we need to subtract it from our total. How many electrons did we just put down? 8. 2, 4, 6, 8, right? Each one of those lines represents a pair of electrons. So that means we need to subtract from our total here 8. So now we still have 24 electrons that we need to put down on the board here. We haven't used up all of our electrons yet. So we're going to ask, do any valence electrons remain? Yes. All right, what do we do then? What we're going to do is we're going to go around the outside and we're going to complete the octet of all of our substituent atoms. All right? So the first thing we do with these leftover electrons is we're going to look at our constituents, the ones on the outside, and we're going to make sure they're all happy, make sure they have a complete octet. All right? And how we're going to do that is by laying down electrons as lone pairs. So this fluorine right here wants to have how many electrons in its octet? 8. And how many does it currently have? Just 2. So I need to complete the octet of this fluorine by laying down another 1, 2, 3, 4, 5, 6 electrons as lone pairs. So now this fluorine's happy because it's got a total of 2, 4, 6, 8 electrons in its octet. All right, so we connected our central atom to these constituents with these single bonds, but we still had some electrons left over. What are we going to do with those leftover electrons? We're going to make sure that all of the atoms on the outside are happy. All right? So each of these fluorines has just one single bond associated with it, so they're each going to need 3 lone pairs, total of 6 lone pair electrons. So once we do that, we need to deduct from our total here. All right, so how many electrons did we just lay down if we put 6 on 4 different elements? 6 times 4? The 24. So now we've used up all of those electrons. So we're not allowed to put any more on the board here. All right, so now we got to say, all right, do we have any left? No, none are left. So now we're just going to make sure that all of our atoms have a full valence, have a complete octet. All right. Our fluorines, we just added these electrons to make sure that they were happy, to make sure they had the complete octet, right? So each fluorine, we can convince ourselves, has 2, 4, 6, 8 electrons in its octet. All right, so our fluorines on the outside are happy. Now we just got to check our central atom carbon. This has 2, 4, 6, 8. So carbon's also happy. All right, so we have all of our electrons on the board. We have all of our atoms with a full octet. So this is the Lewis structure for this carbon tetrafluoride. We're done. Okay, so put down your central atom. You connect everything on the outside to that central atom. If you have any electrons left over, what are you going to do with them? The first thing we're going to do is make sure that everybody on the outside is happy. Complete the octet of all your constituent atoms. All right. Again, going to bump it up in complexity a little bit. We're going to do NH3. Okay. I want you to take it through these first few steps here. Total the number of electrons we have to work with. Put down your central atom and decorate it with these constituent atoms. Draw in your single bonds and total up the number of electrons that you put down on the board. right, so we got a total of how many electrons to work with? 8. All right, we're going to put down our central atom, the nitrogen. We're going to put our hydrogens around it. All right, so first of all, it really does not matter how you orient these hydrogens around this nitrogen. If you put this one down here, or you had it over here, or you had them equally spaced out like a triangle, it really doesn't matter. All right, your Lewis structure is not telling you about the shape of this molecule. We'll talk about how we figure out the shape of the molecule later this week. Your Lewis structure is telling you where the electrons are, who's bonded to who, where the lone pairs are. As long as you have that correct, the spatial arrangement on the page is irrelevant. All right, so I'm going to put down these hydrogens, and I'm going to connect everything with a single bond. All right, how many electrons did we just put down? 6. So now we still have 2 left over. Okay, and we said that what we're going to do first with those leftover electrons is to complete the octet of all the constituent atoms, of everybody on the outside. Okay, so how many lone pairs should I add to this hydrogen to complete its octet? None, right? Because hydrogen only has 2 electrons in its octet. It's already happy with that single bond. You can't be adding any lone pairs to it, or you would exceed its octet. All right, so in this particular case, everybody's on the outside is already happy. So now what do we do with these leftover electrons? Do we have any left over? Anything left over, you're going to put on the central atom. All right, so what do we do with leftover electrons? First, we make everybody on the outside happy. If there's anything left over, then it goes on the central atom. So in this case, my 2 leftover electrons here, I'm going to put on that nitrogen atom, on my central atom. So that takes us down to 0 here. Now we just got to check, is everybody happy? Our hydrogens, we said, only wanted these 2 electrons in its octet. So just that single bond makes hydrogen happy. I got to look at my central nitrogen here. Nitrogen has 2, 4, 6, and with that lone pair, 8. So is the nitrogen happy? Yes. Cool. So here is my Lewis structure for this compound here. Cool. All right. Before we go on into the next sort of level of complexity here, let's pause and do a few examples here. I want you guys to work through these on your own. All right. so I totaled up my number of electrons that I have to work with here, 20. I'm going to put the least electronegative element, except hydrogen, in the middle, and I'm going to put the other ones, my constituent atoms, around the outside. Again, the order in which you put your hydrogens and your bromines doesn't matter. My bromines could be on opposite sides, they could be right next to each other. Doesn't matter how you orient it on the page. Okay? I'm going to now connect everything to my central atom with a single bond. All right, so that means that I just laid down 8 electrons. So I still have 12 more to work with here. What are we going to do with those leftover electrons? Which element are they going to go on here? My bromine. My bromines aren't happy, right? My hydrogens are perfectly fine with their one single bond, but my bromines need a full octet of 8 electrons. Currently, they only have these 2 from that single bond, so I'm going to make them happy by putting in lone pairs to complete the octet. All right, so that makes that bromine happy. That makes that bromine happy, right? Now my bromines both have 2, 4, 6, 8 pairs of electrons in their octet, I guess total electrons in their octet, so my bromines are happy. I've used up all my electrons here. I don't have any more to lay down. So now I just need to make sure that my carbon's happy. Carbon also wants that full octet of 8 electrons. So 2, 4, 6, 8. Okay, my carbon's happy as well. So here would be my structure for this molecule. Okay. Phosphorus trichloride here. We calculate it's got a total of 26 valence electrons, 7 from each of those chlorines and 5 from the phosphorus. I'm going to put down my central atom, decorate it with those chlorines on the outside. Okay. I'm going to connect everything to that central atom with single bonds, 2, 4, 6 electrons worth of single bonds here. So now I'm down to 20. The first thing I'm going to do with those extra electrons is put them on which element? The chlorines, the outside first, all right? Make sure to make the outside happy first. So each chlorine needs 8 electrons in its octet. So I'm going to have to complete with these lone pairs here. So if I put 3 lone pairs, I got a total of 2, 4, 6, 8. All right, so I'm just going to go around and do that to each chlorine. All right, so 3 times 6 would be a total of 18. All right, so now I made sure that everybody on the outside was happy, but I still have these 2 electrons left over. Anything that's left over is going to go where? The central atom. So this lone pair here will go on that phosphorus atom. I'm going to make sure everybody's happy. I made sure the chlorines were happy with those 3 lone pairs. I need to make sure my phosphorus is happy. 2, 4, 6, and that lone pair brings it up to 8. So my phosphorus is happy, and now I've used up all my electrons. All right. Okay, cool. So starting out with our formula, we're going to total up our number of valence electrons, put down your central atom, and connect everything to that central atom. If there are any leftover electrons, first you make everybody on the outside happy. If there's anything left over, it goes in the middle. All right, so let's do another one here. All right, up until now we've seen only single bonds, but we talked about these double and triple bonds. So how is that going to factor in here? So let's do another formula, another compound. Sort of reset our flow chart here. All right, we're going to do CH2O. Okay, you can get all the way through this step here. All right, so we total this up. We got 12 electrons, which is what is going to be my central atom here in this compound? The carbon. You'll notice that 99.9% of the time, the central atom is listed first. The one big exception that comes to mind is water, all right? But 99% of the time, our central atom is that one that's listed first in our formula. All right, so I'm going to put my carbon, or my hydrogen and my oxygen around my central atom. I'm going to connect everything with these single bonds. All right, that means that I just put down a total of 6 electrons. So I have 6 more to work with here. All right, and those leftover electrons I'm going to first put where? The oxygen, right? I'm going to make sure that everybody on the outside is happy. My hydrogens are already happy. So I can complete oxygen's octet with these 3 lone pairs. And that means that I put down a total of 6 electrons here. All right? So now I'm done with my electrons here. I'm going to look and we're going to say, all right, great. Is everybody happy? Does everybody have a complete octet? No. Who's not happy up here? That's central carbon. But we have a problem. I can't just go putting on a lone pair down here because I don't have any more electrons to work with. I already put down all the electrons that I can on the board. So we're not allowed to just willy-nilly add electrons to make everybody happy. Okay? So what are we going to do here? We have our carbon that's mad. We don't have any more electrons to work with. How are we going to do this? We're not allowed to put any new electrons down. What we are allowed to do is to reshuffle what's already on the board. All right? And in particular, if I take this lone pair off of this oxygen and I bring it down here and make it into a bond, right? Now my oxygen, it still has that pair of electrons associated with it. It didn't lose any electrons when I did that. My oxygen still has a total of 2, 4, 6, 8. But now carbon also gets to count that pair of electrons towards its octet. Carbon now has 2, 4, 6, 8. All right, so what are we going to do if we get to a point where all of our atoms do not have a full valence? We're going to remove lone pairs from the constituent atoms and replace them with higher order bonds. Now if we check, everybody's happy. Okay, so just to back it up here. We got to this point where we had all of our electrons on the board, but our carbon was not happy. Okay, we're not allowed to add any more electrons. So what we're going to do is reshuffle what's already here. In particular, we're going to take this lone pair and move it down to create a higher order double bond. All right, now I have a carbon-oxygen double bond, and everybody's got a complete octet. All right, let's do another example here. 2NHS. All right, so I put my nitrogen in the middle and connected the hydrogen and the sulfur with a single bond. That was then a total of 4 electrons that I put down with those covalent bonds. So I got 8 more to go. The first thing I'm going to do with those 8 is to make everybody on the outside happy. So I'm going to make my sulfur happy by adding these 1, 2, 3 lone pairs. That takes me down to 6. That was 6, so that takes me down to 2. Anything left over, I'm going to put central, so the nitrogen. Okay, so now I've used up all my electrons, but am I done? No, what's not happy here? My central atom. And I've already used up all my electrons, so I can't be putting down any more electrons on the board. The only thing that I can do is reshuffle, right? So I can take one of these lone pairs from this sulfur and bring it down here to make one of those higher order bonds a double bond. Okay? And when I do that, my sulfur still gets to count that pair of electrons towards its octet, but now nitrogen also gets to count, that pair of electrons. 2, 4, 6, 8. Cool. All right, so what if we had a compound formula like Cn-1? Right? We got this net charge in our formula here. Okay, this net charge means that I have 1 extra electron compared to the amount of protons in here, right? So when we total up our number of electrons to work with, we're going to have to account for that extra electron there. So when I'm totaling up my electrons here, I'm going to have the number of electrons from carbon, number of valence electrons, which is the 4, plus the number of electrons from nitrogen, 5, plus that extra 1 that I get from my net charge. So if I were to total up the number of valence electrons that I have in this compound here, I have a total of 10 because I'm going to account for that extra one that I have because of the net charge on that ion. All right, so given that we have this net charge giving us a total of 10 valence electrons, see if you can't complete this Lewis structure here. All right, there's only 2 elements, so we can consider to be carbon our central atom since it's the least electronegative, but really there's just going to be those 2 on the page. All right, so if I put down that one single bond, that would be just 2 electrons, so I have 8 left over. I'm going to start by making my constituents happy first. So my nitrogen is going to get these 3 lone pairs. I still got 2 left over, so they're going to go on my central atom, my carbon. All right, so now I have all of my electrons down on the board here. But am I done? No, my carbon only has these 4 electrons in its octet. It's not happy. So what I'm going to do is reshuffle what's already on the page here. I'm going to take one of these lone pairs from the nitrogen and move it over here to become a bonding pair. So now I'm done. No, my carbon's still not happy. So what am I going to do now? I'm just going to play that game again. I'm going to take another pair of electrons from the nitrogen and bring it down to form what we call a triple bond. And now if I look, both of these elements are happy. They both have 2, 4, 6, 8 electrons in their octet. 2, 4, 6, 8. And so this is my Lewis structure for this cyanide ion here. Okay? Cool, so now we got the basics down. We'll sort of learn how to analyze these structures a little bit more and draw some of the more complicated ones next class.